One of Earth's most amazing substances is one of its most common: water. Over a narrow range of temperature, water can be either a liquid, a solid, or a gas. And in the atmosphere, it takes all of these forms. Here it's changing from a gas to a liquid and back to a gas. So where does all of this airborne water come from? Actually, most of it is picked up over warm tropical oceans. This is because the higher the temperature, the more rapidly water evaporates. As the water evaporates, heat is carried away with the escaping vapor. That's why you cool off. It's hard to imagine the vast amount of water vapor entering the atmosphere through evaporation. The actual amount depends on temperature. The warmer the air, the more water it can hold. So as moist air is cooled, its vapor will begin condensing, an effect often seen on the surface of a cold glass, or just about anywhere moisture-laden air is cooled. Cooling of air that has become saturated with water vapor also produces clouds and fog. For example, when moist air at the lake's surface cools, you see the result: a thin fog. The temperature at which water vapor begins condensing is called the dew point. Clouds and fog mean the dew point temperature has been reached. Of course, dew point temperature also depends on how much water vapor is available. And that can vary tremendously, from about 4% here to less than 0.25% here. So at least two things affect the formation of clouds: amount of vapor present and temperature. But what if you could put a piece of this cloud stuff under a microscope? Would it show any kind of structure? With a plastic slide, some ice, and a breath tube, you can observe what clouds are made of: tiny spheres of water. If these microscopic drops were suspended in air, they'd be called cloud droplets. Cloud droplets can form or vanish in seconds, depending on the dew point. This rapid shift of water between vapor and liquid is at work wherever clouds are building or dissolving, something that can be observed more easily if time is sped up photographically. The results make normal activities look a little strange, but time-lapse studies are useful for observing the behavior of clouds. For example, these clouds are forming over a mountain range, but as they drift away over the desert, their cloud droplets begin evaporating in the warm desert air, cloud behavior that is hard to see in real time. Cloud droplets form or vanish, governed by temperature and amount of water vapor. But there's one more ingredient in a cloud droplet recipe: microscopic particles within these droplets that act as a starting point for condensation. There is usually no shortage of these airborne particles, called condensation nuclei. Smoke and industrial pollution contribute heavily. And all of these microscopic particles circulate, ready to play a role in cloud building. Even far from smoke or pollution, a wave-swept coast can supply seeds for clouds. When sea spray evaporates, tiny airborne crystals of salt are left floating in air, nuclei for cloud droplets. Clouds, masses of airborne water droplets, constantly forming and vanishing, depending on temperature, the amount of water vapor present, and the availability of condensation nuclei. But a cloud droplet is very different in size from a raindrop. If this sphere represents a raindrop, then this represents a single cloud droplet. And this speck within the droplet, a condensation nucleus for that one cloud droplet. One way raindrops form is that cloud droplets start bumping into each other, larger ones gobbling up smaller ones as they fall through a cloud. Another rain-making process begins high in clouds where it's cold enough for ice crystals to form. Dropping into warmer air, the frozen water melts, forming raindrops. Mountains can have a significant effect on clouds. This is because air, forced upward by the mountain, cools, causing its water vapor to condense. Driving up a mountain road, the higher you go, the denser the clouds become, producing rain. And as you go higher, rain turns to wet, mushy snow. Climbing the mountain, temperature falls rapidly and the snow gets heavier. But then, surprisingly, at the summit, precipitation may stop. The other side of the mountain is clear and inviting. What happened? Uplifting of air by the mountain produced such effective cooling that it condensed out most of the water as rain and snow, leaving clear air on the backside. So sometimes, when it's storming on the windward side, this sunny backside with its dry, powdery snow is a good place to be. From a distance, you can see the puffy cumulus clouds that formed over the mountain. A cumulus that becomes large enough to produce heavy precipitation is a cumulonimbus, or thunderhead. A cumulonimbus can become a towering giant, clearly visible from 200 miles up. A thunderhead gets started when moist air begins to rise, setting up a kind of circulation that draws in more vapor-laden air. The overall process is called convection, which means a kind of circulation produced by heat. It's easy to create a laboratory model of a thunderhead using a small tank of water, a heat source, and colored dyes that make the convection patterns visible. Directly above the heat source, a column of fluid, made visible by the dye, is set in motion. Then, as the rising column cools, a process sped up by ice at the sides, the water begins sinking. These vertical currents, started by heat, show the kind of flow patterns found in thunderheads. A cumulonimbus may get started when warm, moisture-laden air starts to rise. But what keeps it building is heat generated within the cloud itself by the process of condensation. The more vapor a cumulonimbus converts into water droplets, the more heat is released. And this heat of condensation is what drives these huge convection clouds. Once started, a thunderhead acts like a chimney, pulling in moist air and growing until winds aloft tear away its top and stop further upward cloud building. A big cumulonimbus can be a dangerous cloud. Its turbulent, lightning-charged interior still contains mysteries, but there is one point of agreement. If you're piloting a light plane, stay away from thunderheads. But carefully flying through parts of a thunderhead is exactly what these atmospheric scientists intend to do. They're using a modified sailplane and a good deal of experience to probe the cloud and find out more about processes going on in its dark interior. A sailplane's advantage over powered craft is that it cannot itself become a source of contamination when collecting samples of condensation nuclei from within the cloud. But the pilot has another advantage, for his craft is a sensitive instrument that can feel out air currents, allowing him to stay in the cloud, radioing back a stream of data on conditions within the thunderhead. Spreading over the sky at about the same levels as the tops of big thunderheads are wispy clouds that produce no rain or snow, at least not directly. That's because most of the water in these cirrus clouds is in the form of ice. From above the atmosphere, cirrus clouds can have a rippled appearance. Although they produce no rain or snow, there may be a relationship between cirrus clouds and the denser clouds that do. One theory is that cirrus layer ice crystals may be carried into storm clouds and become nuclei for snowflakes. In temperate regions, much of the snow and rain falls from layered clouds called stratus, formed by air that rises slowly and evenly. Stratus layers are often formed over oceans and may cover vast areas, becoming part of the great weather cycle that brings water to the land. Drop by drop, channeling into countless streams, water is returned to its ocean reservoir, only to be picked up again and condensed into clouds.